Hi everyone, welcome to part 3 of this week's session looking at regression. So in this final part I'm going to start by considering how we might include categorical predictors in regression. So I talked initially about regression being a good analysis option if our predictors are continuous, but one of the strengths of regression is that it's possible to include combinations of continuous and categorical predictors in our model. So how do we include categorical predictors rather than continuous predictors? Well, one example might be a categorical predictor with two levels, a binary predictor. Well, we've already considered one of those in the analyses that we've run a little bit earlier. Participant sex in the analyses was a binary categorical variable. So with binary categorical predictors, a key thing to remember is that their interpretation depends very much on how those categorical variables are coded. Those categorical predictors are coded. In our case, it was coded as follows. Female was coded as 1, male was coded as 2. So what does that mean for the regression coefficient? The regression coefficient represents the effect on the dependent variable of being male rather than female, of being in the second category compared to the first category. Okay. If we coded it the other way around, if for example male was coded as 1, female coded as 2, then the coefficient would represent the effect of being female rather than male. Okay, just to put that in slightly more concrete terms, here is the outcome of the multiple regression that we ran last time round. The coefficient is 0.22, and because of the way it was coded, female is the reference category, coded as 1, male is the comparison category of 2. So the coefficient therefore means that being male rather than female is associated with an increase in commitment of 0.22 units. And that happened to be a non-significant effect. So that effect of being male rather than female on commitment is non-significant. So what about categorical predictors that have 3 or more levels? Okay. Well, let's say we go back to that core research question. Our researcher looking at the effect of identification with an organization on commitment. Let's say they also want to take into account whether working in different departments in the organization also predicts organizational commitment. Let's say in the organization they're looking at, there are 3 different departments: the sales team, the development team, and the IT team. Okay. Now, for coding purposes, we can assign numbers to these. Let's say sales is 1, development 2, and IT is 3. But that numbering is arbitrary and meaningless to analyze in itself in terms of their numerical values. So what we do instead is create dummy variables. In other words, we create 3 variables, 1 variable for each level, okay, that represents whether or not participants are in a particular category or level of that predictor. Okay, we've got 3 categories, therefore there'll be 3 dummy variables. And that allows us to test, firstly, the significance and the explanatory role of the variable as a whole, the effect of department, as it were, but also the effect then of being in a specific category within that variable relative to a reference category. Now, one of the things that hopefully you'll recall from last year is that when we are using dummy variables to represent a categorical variable, one of those dummy variables is dropped from the analysis. So if we have 3 levels of our categorical variable, therefore 3 dummy variables overall, only 2 of those get entered as a predictor in the analysis. And the reason for that is if we entered all 3, then we would have a case of redundancy, where scores or people's level or score on one of those dummy variables could be perfectly predicted from knowledge of the other 2. If you know that somebody is not in the sales or development team, you know they must be in the IT team, etc. Okay, so in order to avoid redundancy between predictors, one of the dummy variables for a categorical variable is always dropped or excluded from the analysis. So let's have a look at an example. Let's go back to our data file. So I'm going to run our model again. I'm going to enter, and this will be familiar, commitment once more is our outcome variable. We've got our 4 covariates, our continuous predictors. Sex is a factor, and now team is also a factor. So team is coded to have 3 levels: sales, development, and IT. So I'm going to enter that as a factor. Okay. It hasn't automatically included them in blocks. So what I'm going to do first of all, before I get to that, I'm going to ask for the usual things we want in terms of model fit and the coefficients, information about the coefficients. And what I'm going to do is enter all of the predictors in block 1 with the exception of team. Okay, so I'm going to put annual salary, identification, job satisfaction, age, and sex. And then our 3-level categorical variable goes in its own block. Okay. Now what that gives us is the final model where we have the individual coefficients for the dummy variables. In this case, IT is the reference category. That's the one that's been dropped from the analysis. So the category that's dropped from the analysis is the reference category, okay, against which each of the other levels is compared. So what this shows, for example, is the effect of being in the development team as opposed to the IT team, or in the sales team as opposed to the IT team. Okay. A key thing here is that you can change very easily in Jamovi what the reference category is. If you didn't want it to be IT, you can simply go to reference levels and change it from IT to sales, say. Okay. That means that sales is now dropped and becomes the reference category. So now you have a test of the effect of being in the IT team versus the sales team, and the development team versus the sales team. Okay. Now, the other thing to point out is that this is an example of a hierarchical linear regression. And the reason for that is, as well as being interested in the individual effects of being in specific categories, we're also interested in the effect of team as a whole, team as a variable. Does team membership have an impact overall on commitment to the organization? So the reason we run it as a hierarchical regression is that it allows us to look at the specific contribution of team when taking all the other variables into account. Okay, so it gives us this estimate here. The model comparison table is a comparison of a model that doesn't versus a model that does include team as a variable. Now we've got a value for the adjusted R-squared. We've got an estimate here of the amount of variance specifically accounted for by team. It's not very much, less than 1%. And a test of whether that variance explained by team is significant, which it isn't. Okay, so let's just pick out a few of those key bits of information again. So we've got our model comparison table showing that adding department or team as a variable does not significantly improve the model fit. Okay, less than 1%, 0.3% increase in variance accounted for, which is very clearly not significant. So team as a whole, department as a whole, doesn't seem to predict commitment to the organization. Then the coefficients for team as a variable, okay, development versus IT. IT here is the reference category as it was by default. So being in the development team as opposed to IT, or the sales team as opposed to IT, were not significant, as you would expect from the overall non-significant effect of team. Okay. In terms of interpreting the coefficients, at least descriptively, the negative coefficient here suggests that overall being in the development team is associated with slightly less commitment than the IT team, and being in the sales team, a positive coefficient, means that being in the sales team is descriptively associated with being more committed than being in the IT team. Okay. However, those effects are nowhere near significantly different from 0. So yeah, they shouldn't be interpreted as representing a real effect. So that's just to say that the interpretation of the coefficients in terms of their sign, positive or negative, is similar to as it is for other predictors. So let's turn to the final thing that I'm going to cover in this session on regression. And that's going back to one of the big challenges that I outlined in part 1, which is the difficulty of inferring causality or causation between variables in regression. So that difficulty, just to remind you, is that there might be very good reason to hypothesize that one variable A predicts or affects variable B, but if we've only measured rather than manipulated those variables, variable A specifically, then we can't be sure that the relationship is causal. For example, the relationship between A and B might just reflect the fact that they are both caused by another factor, a third variable that isn't actually measured in the study. Or indeed, the causal relationship might be the reverse. It might be B affecting A. So let's take that most basic research design that we considered at the start. We might have hypothesized that identification will positively predict commitment, but another researcher might come with a different hypothesis. It might be that they suppose that commitment is what predicts identification. The causal relationship is entirely the reverse. Now, with a given data set, the data set that we looked at, for example, those two different linear regression analyses where you're swapping the predictor and the dependent variable would be indistinguishable. Okay, these would give you an identical beta statistic, beta coefficient, an identical t statistic and p-value, and an identical r squared. Okay, so statistically speaking, these models are indistinguishable, even though theoretically they're saying very, very different things. So one possible way of addressing this is through adopting longitudinal research designs. Okay, so the thinking here might be that, well, if one of the criteria for establishing causality, causal relations between variables, is that the cause precedes the outcome in time, then perhaps an answer is to measure the predictor and the outcome at different time points. For example, measuring the predictor 1 week or a month or a year before you measure the outcome variable. So we might have a slightly augmented design here where the researcher measures identification at one time point and then measures the outcome variable commitment a month later. Okay, that's still a problem though. Far from ideal, because the outcome commitment could at an even earlier time point, time 0 say, a month before identification, have been predicting identification. Okay, so this in itself, this relationship, if you find it, this association, could just reflect the fact that commitment was predicting identification at an even earlier time point. So a solution of sorts, and I say of sorts because it, in the end, it isn't actually a solution. It's not a foolproof way of inferring causality, but it does help. It can give you a better indication than other methods, and that is cross-lagged analyses based on cross-lagged panel designs. Now, the key thing here is that you measure both the predictor and the outcome at 2 or more time points. So rather than just measuring the predictor at one time point and the outcome at a second time point, you measure both of them at both time points. Then you regress the outcome at time 2 on the predictor at time 1. So let's say commitment at time 2 regressed on identification at time 1, but also controlling for the outcome variable measured at time 1. So you would have a model where commitment at time 2 is predicted by identification and commitment both measured at time 1. So the link or the association between commitment at time 1 and commitment at time 2 is called the autoregressive effect. It's a variable being regressed on itself. That's the autoregression bit. It's being regressed on itself at an earlier time point. Okay, so an autoregressive effect here, a particular type, a little bit of terminology or jargon. The autoregressive effect is the effect of a variable being predicted by itself measured at an earlier time point. Okay, so in this design now we've got identification at time 1, predicting commitment at time 2, while also controlling for commitment measured at time 1. So what's the logic here? Well, unless the outcome variable at time 1, let's say commitment at time 1, unless that explains 100% of the variance in time 2 commitment, the outcome at time 2, then it means that scores have changed over time. Okay, let's say it explains 60% or 70% of the variance in commitment at time 2. That means that 30 or 40% of the variance is different, okay, than it was at time 1. Therefore, any variance not explained, that 30 to 40%, represents a change score. Unexplained variance left over when you regress it on time 1 commitment is change. Now, this is where adding another predictor at time 1 comes in. If another variable measured at time 1 in this model predicts the time 2 outcome, let's say identification at time 1, predicts commitment at time 2, what it's doing is predicting change in the outcome, commitment, from time 1 to time 2, and that change must have occurred after the time 1 variables were measured. Okay, so that's the key thing. In a model like this, where you're including or controlling for a measure of the outcome variable measured at an earlier time point, the same time point as your predictor, then what you're predicting is change in the outcome variable that would have occurred after or since the time 1 measures were taken. Okay, and it's that aspect of it that helps with the inference of causality. Now, a second part of the fully cross-lagged design is that you can also do the same model or run the same model or the equivalent model looking at the predictor variable. You can regress the time 2 measure, time 2 identification in this case, okay, on the time 1 outcome variable while controlling for the predictor at time 1. Now, in a sense, this is the same model. You've got identification and commitment at time 1 as predictors, but we've just changed the outcome variable. Okay, we've put identification as the outcome rather than commitment. So the logic here is that, well, if the outcome variable at time 1, let's say commitment at time 1, doesn't predict identification at time 2, then the data don't support the alternative causal relationship. Okay, so we might see that the predictor, identification, predicts change in commitment, but in this model, commitment does not predict a change in identification. So if there's a causal relationship, it also looks like it's in one direction. Okay, identification predicts change in commitment, but commitment does not predict change in identification. Okay, so let's see that in action. So I've got a data set here where we have identification and commitment measured at 2 different time points each. So we've got identification at time 1, T1, identification at time 2, T2, and commitment at time 1 and time 2 respectively. So to run these cross-lagged analyses, we just need 2 pretty straightforward regression analyses. So we go to regression, linear regression. In both of the models, we have the same predictors. We've got the 2 time 1 measures, time 1 commitment and time 1 identification. Okay. And the outcome variable in this case, in the first analysis, is going to be commitment at time 2. So the model looks at whether identification at time 1 predicts commitment at time 2 while controlling for commitment measured at time 1, the same time as identification. Let's ask for the usual stuff: adjusted R-squared, the overall ANOVA test, the confidence interval for the unstandardized estimate, and the beta coefficient. Okay. So, what does this show us? Let's look at the coefficients table. Commitment predicts commitment at time 1, predicts commitment at time 2. Okay, very clearly. Highly significant, as you might expect. But it's far from 100%. Okay. Overall, the entire model only explains 44% of the variance. So there seems to have been quite a bit of change in scores of commitment over time between time 1 and time 2. Now let's look at the coefficients for identification. Does identification at time 1 predict change in commitment between time 1 and time 2? Well, yes it does. That coefficient is positive, so it means that identification at time 1 predicts change in commitment between time 1 and time 2. Okay, because we have controlled for commitment at time 1. So again, just that terminology, the effect of commitment on itself is the autoregressive effect, and then this is the predictive effect of identification. Now let's do the reverse model. Now because it's exactly the same, I'm just going to go to Analyze, right click on Analysis and Duplicate. Okay. And now all I'm going to do is swap out commitment at time 2 for identification at time 2. This is the model that tests the reverse causal effect. So this time around, identification is the outcome variable. The autoregressive effect of identification on itself from time 1 to time 2 is highly significant, but the effect of commitment at time 1 is not significant. Okay. Commitment at time 1 does not predict change over time in identification. So between the two models now, we've got one that shows that, or indicates that identification predicts change in commitment over time. Okay. But commitment does not predict change in identification over time. And the coefficients are just interpreted in the usual way. So these are the unstandardized coefficients. If you wanted to report the betas, they're there as well. Beta coefficients. Beta coefficients. Okay. So we might report that fully cross-lagged model as follows. We can draw it as a figure. We're including the coefficients from those two different models combined. All right. So the ones, the arrows pointing to commitment at time 2, they come from that first model. Okay. That's the autoregressive coefficient, 0.61, highly significant. And identification also predicts commitment, change in commitment between time 1 and time 2. The second model, where identification at time 2 was the outcome, provides the coefficients for these arrows, these paths, going to identification at time 2. Again, a highly significant autoregressive effect, identification predicting itself, but this time a non-significant path from commitment at time 1. Commitment at time 1 does not significantly predict change in identification. So that's a cross-lagged model, and that's one of the ways in which design-wise and analysis-wise we can try and infer a little bit more about causal relations between variables that we can't directly manipulate for whatever reason by using longitudinal research designs. And that approach can help us, it can increase confidence about the nature of causal relations amongst variables, but this is the caveat, not entirely. There's always going to be residual, often considerable, residual uncertainty that the relationships are causal, because unless we directly manipulate variables, there is still going to be a degree of uncertainty about the causal relationship. Okay. Are these variables, for example, confounded with other variables that we haven't measured, for instance? So all those things are still at play in this research design, this sort of longitudinal cross-lagged research design, even if it does in and of itself give us a little bit more of a handle on what the relationships between them might be. Okay, that's it for this session on regression. Next time round, we're going to be taking some of the principles that we've talked about this time and introduce mediation and indirect effects. All right, thanks very much, and join me then.